Hi guys, welcome to the first video on amines, and we're going to start off with doing a bit of basic amines. So we're not going to go into too much detail, but we'll have a good overview of what we will, we'll get into it. So we'll probably want to start off with, especially for those who don't know what an amine is what exactly is an amine, and to know that, we need to know what ammonia is. And I'm sure you do know what ammonia is if you're researching amines. But if you don't, then obviously go and know what ammonia is. But it's just a compound. It's just a molecule, NH3, and a amine is a derivative of ammonia, the NH3, whereby one or more of these hydrogen atoms have been replaced by an ethyl or an aryl group. If you don't know what an ethyl or an aryl group is, an ethyl group is just something like methyl here, or it could be like ethyl or pentyl, and a whole load of different, any of them. And an aryl group is more to do with aromatic chemistry, but we'll get into that later. And it's the same concept. There are a few categories of amines. We start off with the most simplest amine you'll ever come across is methylamine. Methylamine is a primary amine. We know it's an amine first of all because the hydrogen here from ammonia has been replaced by an ethyl group. In this case it's methyl, and so we can tell it's a primary amine because it's got one R group. If R meaning the ethyl here. And we say it's primary because it's only got the one R group attached to it, and we represent this with a 1 and a little degree symbol next to that. Yeah, so that's primary amine, methylamine. And then we've got a secondary amine. Just to go through, we've got secondary amines. That's when two hydrogens from the ammonia have been replaced by R groups. Here it's two methyls again, a methyl again, because it's very easy to draw, so, Secondary amine, that's represented by a 2 with a little degree symbol, and you can also have tertiary amines. Tertiary amines is when all three of the hydrogens from the ammonia have been replaced by R groups. So here I've replaced one hydrogen with a methyl, another hydrogen with a methyl, and we've replaced the last hydrogen here with an ethyl. If you're going to name this, it would be ethyl dimethylamine. The reason we put the ethyl before the methyl in this case is because when you name amines, you name them with the R groups in alphabetical order. Ignoring the di, because that just means there's two of them, you're focusing on the M, because that is the R group, not the di. Don't focus on D. D is not included in this alphabetical ordering system. So, you have ethyl, E is before M in the alphabet, so it's ethyl, dimethyl, amine. It's a tertiary amine, and that is, as you could guess, represented by a 3 and a little degree symbol. So there you go. They're the three ones you'll come across most often, but you can also come across, it's not really an amine, but it's an ammonium salt, but it kind of falls into this topic. This is when the lone pair of electrons here might form a dative covalent bond, or a coordinate bond, or whatever you want to call it, with another R group, and become an ammonium ion. It becomes an ion because this nitrogen here, when nitrogen has 4 bonds connected to it, it develops a positive charge, and that's to do with a load of stuff like hybridization and things. And if you want to know more about why that happens, I'll put a link in the description for the website, a website that explains it quite well, but it's not in the syllabus, so we won't focus on it. So here we go, here's an ammonium ion being formed because we've had another R group come and attach itself. So we've gone from this, say, and we have had this R group, the propyl R group, C3, 3 carbons, come and attach itself. It's given it a positive charge, making it a positive ion, which is unusual because so far most of the cations you've come across have only been metal ions for a lot of the students watching this. Um, because we learn about ionic bonding in and salts, and that usually involves a metal and a non-metal. Pardon me. And I've just included a chlorine here, a chloride ion, just to show that it forms ionic bonding with a chloride. It could be a bromide, an iodide, or whatever, to form a salt. If you're going to name this, you'd call it, it's the same process as before, so alphabetical order with the R groups, ethyl, dimethyl, because there's two methyl groups, there's an ethyl group, propyl is here, so ethyl, dimethyl, propylammonium, no, that's wrong, ethyl dimethyl propylammonium chloride. Instead of the amine, it's been replaced with ammonium because it's no longer an amine. It has nitrogen with 4 bonds. It's a derivative of the ammonium ion. This one here, NH4, and N plus H4, I should say. I've just separated the words so it's easier to see here because it looks like a big word, doesn't it? But it's quite simple. And this is a quaternary ammonium salt. Quaternary because it's got 4 bonds to the nitrogen, and that's represented with a 4, like the others, with the other numbers, like the tertiary's got 3. This one's represented with a 4 and a little degree there. And I've included this slide because just to show, this is the aryl groups I was talking about earlier on. So an amine is a derivative of NH3, whereby one or more of the hydrogens has been replaced by an ethyl or an aryl. And these are aryl groups. This is a benzene connected to nitrogen here, and that will form phenylamine. Phenylamine is formed when a benzene is attached to a ammonia. It replaces a hydrogen in ammonia, and it's the same as the primary here. This primary here, the methylamine, it's just got a methyl group attached to it, and it's a primary because it's got one R group attached to it. Whereas this has got one benzene ring attached to it. It's still a primary because only one hydrogen's been replaced, except it's got an aryl group instead of an ethyl group. So not too much to understand there. And here I've just shown, you can have diphenylamine where you've got 2 aryl groups. It works exactly the same as the other ones, and this would be a secondary because 2 hydrogens have been replaced by an aryl group here. You might see in older exam papers and things phenylamine being referred to as alanine. Alanine is just an older name given to it before the IUPAC name naming system was introduced. A little bit about the shape of ammonia. This shape will apply to amines, so it will apply to all the amines as well as ammonia because it's derivative of ammonia. So this might be an R group here, and it'll be the same. So the nitrogen here, we know nitrogen has 5 valence electrons in its secondary shell, second shell, and 3 of them are being used up by these hydrogens. So we have 2 left, which form a lone pair. And as we know, lone pairs reduce bond angles by 2.5 degrees. If this lone pair were to be used, and this were to be like an ammonium ion, like this one here, then it would be a tetrahedral shape with bond angles of 109.5 degrees. But because it's a lone pair, it reduces this angle to 107 degrees because it deducts 2.5 from 109.5, making 107 degrees. And this shape is a pyramidal shape. Pyramidal, I've done a little drawing here, it's not very well done, but get the idea. There's lone pairs on top pushing it down into a pyramid sort of shape. That's not the right pyramid. It should be only have 3 faces, but you get the idea. Here we're just going to talk about the electronegativity of nitrogen, talk about the polarity of the amines. nitrogen is quite an electronegative atom. It has an electronegativity of 3, and so this means that when a hydrogen is bonded to it, it can pull the hydrogen's electrons towards itself and create a permanent dipole in the hydrogen. And the nitrogen here, it has a lone pair of electrons, and so a hydrogen bond can form between the nitrogen and the positive hydrogen with the delta plus there. I'm sure you've probably already gone over hydrogen bonding, so I won't dwell too much on it, but just so you know, amines will have hydrogen bonds between them. I will say, except for tertiary amines. Tertiary amines, which we can see here, have no hydrogens. There's no hydrogens here, so there won't be any hydrogen bonding present between, say, ethyl dimethylamine. If that were, in its pure state by itself, it wouldn't have any hydrogen bonds present. It would have some weaker intermolecular forces acting. Here we have oxygen. Oh, it's not just a circle. And oxygen has an electronegativity of 3.5. I'm just showing you here in water. There are hydrogen bonds in water, as you probably know. The oxygen pulls in the electrons from the hydrogen and creates a permanent dipole in the hydrogen, which allows for hydrogen bonding in the water molecules, as with amines, except because oxygen has a higher electronegativity, it will form a stronger hydrogen bond because it pulls the electrons in farther towards itself, away from the hydrogen, and the hydrogen will get a stronger positive charge, and so the forces will be stronger between the hydrogen and the lone pairs on another water molecule here. This is an example of how the weaker hydrogen bond in amines affects it compared to its alcoholic counterpart, say. So we've got methylamine here. Methylamine is, I'll go to a slide with methylamine on it. This is methylamine, as we've been over at the very beginning. Primary amine, 1R group, a methyl group. Methylamine, when it's at room temperature, is a gas because it's got hydrogen bonding, but it's fairly weak. Whilst methanol is methylamine's alcoholic counterpart, if you will. It's just a different functional group. It's got the OH instead of a NH2 here. Instead of it's a liquid. And if you're wondering why it's a liquid, it's because the electronegativity here, oxygen is more electronegative than nitrogen. And as you can see, the functional group is different here. We've got an oxygen instead of a nitrogen, which means the hydrogen bonding between the methanol molecules are a lot stronger than the nitrogen hydrogen bonding, which means it has a higher boiling point and will be a liquid at room temperature as opposed to being a gas. The same is true for ethylamine. Ethylamine is also a gas at room temperature, whilst its alcoholic counterpart, ethanol, is a liquid because it's got stronger hydrogen bonding, which means it's got a higher boiling point. Propylamine, from after ethylamine though, we have, say, propylamine, which is the NH2 C3H 7, and it is a liquid. Its alcoholic counterpart is also a liquid, except propylamine is more volatile than its alcoholic counterpart because it has a lower boiling point, because it has weaker hydrogen bondings. So it's a volatile liquid. Yeah. So that's what you need to know with the comparison between boiling points of amines and their alcoholic counterparts. Yeah. amines have a lower boiling point than their alcoholic counterparts because the nitrogen is less electronegative than the oxygen, and so the hydrogen bonding in the amines is weaker than in the oxygen, than in the alcohol molecules. And another note, amines are very smelly. Amines have a very fishy smell. And when you see if you've ever come across a decomposing corpse of an animal, maybe, you'll notice it has quite a repugnant smell. And this is because the proteins in the animal, partly due to the proteins in the animal, are decomposing and releasing amines gases, which, like I just said, are very smelly. They smell like fish. So that might be a question at some point in a test or something. You never know. Solubility of amines. Amines are very soluble in water because, like I said before, they can form hydrogen bonds. And this methylamine here, which is our key example molecule at the moment, is very soluble in water because it forms hydrogen bonds with the water molecules. It's also very soluble in alcohols, for the very same reason that it can form hydrogen bonds with the oxygen in alcohols, and the hydrogen in the alcohol can also form hydrogen bonds with the nitrogen as well. And likewise with water, the hydrogen on the water can form hydrogen bonds with the nitrogen also. So they're very soluble because they like to form bonds, hydrogen bonds together. Whereas oh no, never mind. Even tertiary amines are soluble. Tertiary amines, which we were discussing before, can't form hydrogen bonds with each other because they have no hydrogens to have a permanent dipole anywhere, but they can form hydrogen bonds with things like water and alcohol because the water will have a positively charged or delta positively charged hydrogen here, which will be able to form hydrogen bonds with nitrogen. But it's only the hydrogens from the water and the nitrogen here which will be able to form the hydrogen bonds, which means that tertiary amines are soluble in water, but less so because less hydrogen bonding can form. It also means they've got a lower boiling point because of there are less hydrogen bonds. If we go back to here, this amine here, primary amine, will have a higher boiling point than a tertiary amine and even a secondary amine because it's got two hydrogens here which can form hydrogen bonds with alcohols or water, whereas the secondary amine will have only one hydrogen and a tertiary amine has no hydrogens. The more hydrogen bonding present means that there will be a higher boiling point. So primary amines out of primary, secondary and tertiary amines have the highest boiling point because the most hydrogen bonds are formed. After you've reached a chain of about 4 carbons, so if you have a primary amine, you can have a secondary amine or a tertiary amine, it doesn't really matter, but we focus on primary because it's just simple. Let's say you have a pentyl group attached to this primary amine, to the nitrogen of this amine. This is simply just too long. The chain here is too big, and the solubility of amine starts to drop off after about 4 carbons, after about after like the butyl group, because the massive big booty chain here starts to force its way through hydrogen bonds, because it's a pest. It forces its way through hydrogen bonds and breaks them, so it becomes a lot less soluble because hydrogen bonds don't form as often, or if they do, it's only that temporary because this guy comes along and just poof, goes right through it. I know, what a douche. And to finish off, we've got phenylamine. Phenylamine is less. Still talking about solubility here. Phenylamine isn't very soluble because hold on. because we will go into this more when we talk about aromatic chemistry, but it's because this this benzene ring here is it's got a ring of electrons in the middle. Yeah, it's got high electron density, and we'll go into why when we go over aromatic chemistry. But basically, what's going on here is that the electrons from the nitrogen are being pulled into this ring of electrons. So it stops the nitrogen from forming hydrogen bonds. If you're wondering why, it's because if the nitrogen doesn't have a lone pair of electrons, then obviously it can't. Hold on. Well, actually, we haven't got a good example. It can't. There we go. That's a good example. It can't connect to hydrogen because it's not got the negative delta charge. Yeah, which you know from hydrogen bonding. So I think that's it for the oh well, one more thing. I've been talking about alcohols and waters here, and they're quite soluble in alcohols and water. Amines are. To add, they are also quite soluble in less polar solvents. But we were just focusing on alcohols and water. But they're most soluble in these ones because they can form hydrogen bonds. Otherwise, I think that's it for now. In the next video, we're going to be focusing a bit more on more complicated study behind amines, and we're going to be talking about the base properties of amines and maybe some other stuff if there's time. But this is just a basic covering of amines, and I hope it's been good. Tune in for the next video. Thanks for watching. Bye.